Hi everyone, my name is Hannah Mohammed and I'm here with my group member Ben Crick, and together with Arsalan Beg Menhaj and Hyun-Sik Moon we are NEE 2016 Group 18. Today I will be here to talk to you about a novel crystal that we have synthesized and tested in the lab for the absorption and desorption of oxygen. And advising us for this project was Professor Robert Varon. The reactivity of oxygen makes it important in many facets of industry and research. Some processes or material storage require oxygen to be removed from the environment, and then there are some that need oxygen to be put into the environment. Our product aims to act both as an oxygen scavenger in some situations and possibly an even oxygen source in other situations. But for the purposes of our project, we are focusing on its scavenging abilities of oxygen. Next slide. When looking into the food packing industry, there are a few options that are currently available today. One of which is a very popular disposable ferrous oxide sachets as seen on the slide. Another method used in large-scale food processing or in transport is nitrogen purging. Both of these methods have their downsides. For one, the ferrous carbonate sachet is disposable, which adds to a company's disposable cost, and it also adds to environmental waste. The purging by nitrogen is a good method, although it must be done in batches, so in linear processing, you need to slow down the processing line. And also, both of these methods require constant source of oxygen or for the ferrous carbonate sachet. One area of future interest for our project mentioned earlier is the oxygen storage capabilities. Industries such as welding, healthcare, and underwater work require a source of oxygen, which is today used in something like heavy tanks or in peroxide candles. These solutions can be heavy or bulky and expensive and sometimes dangerous. And these solutions can be, if further testing could be done on our storage crystal, then we can determine that if it could be a viable solution for these processes as well. Our prototype has the ability to both absorb and desorb oxygen with high specificity based on the temperature. During our testing, we used room temperature for our absorption and then 100 degrees Celsius for our desorption temperature. Literature showed that this crystal was able to absorb and desorb with little to no loss of efficacy between cycles. And it also had a high storage density. The crystal also underwent a color change between black and pink between the oxygenated state and the deoxygenated state. Our membrane chosen for the crystal to house it is PDMS, or polydimethylsiloxane, which is permeable to oxygen but is watertight. We were able to achieve a partly reversible binding for our crystal and no color change, which will be discussed later on in these slides. Now I'll pass it off to Ben.
At this point, it's necessary for me to introduce metal-organic frameworks. So a metal-organic framework is a large macromolecule which contains 1 to 4 metallic centers surrounded by and coordinated by a large organic structure. This organic cage is usually a complex of large carbon-based ring structures coordinating this metal center. They're often capable of reversible diatomic gas absorption, and this property has made them the subject of much research recently. They are also found in nature. For example, the heme group in the hemoglobin of our blood, shown above, is essentially one of these structures using iron as the core. Hemocyanin is used by arthropods and mollusks, performs the same function with 2 copper centers. Other similar structures exist in your muscles to store the oxygen, in your brain and nerves to scavenge oxygen and prevent it from degrading your nervous system. So our prototype is a cobalt-based metal organic framework. At room temperature, it aggressively absorbs both oxygen gas and water vapor. It absorbs oxygen down to under 1% when available in sufficient quantities. It's very aggressive at absorbing water vapor. For example, when left overnight in our glove box, it pulled water from the atmosphere so strongly that about half a pound of dryrite, a specific compound intended to be disposable to dry vapor from the air, actually had the water sucked out of it into our product and returned to its original state. This was a much larger reaction than we expected. Now, the important part of our concept is that when heated to around 80 to 100 degrees centigrade, it releases all of the stored oxygen gas and most of the water. Our prototype uses nanoporous PDMS, as mentioned, to allow oxygen and water vapor flux while preventing the excretion of cobalt or potentially toxic aromatic compounds. The size of the PDMS pores can be selected for the customer's needs. So if water is not desired to be absorbed, you can select pores which would allow oxygen and forbid water transport. So the chemistry of our crystal was the main focus of our synthesis and is somewhat complex. The crystal itself is a hydrated nitrate salt of this cobalt metal organic framework. This slide shows the active metal organic cation, which is the active center for oxygen absorption. Emitted are the hydrogen atoms, nitrates, and the coordinated waters. So the two halves of our crystal, you can see it's basically a mirror image, consist of the cobalt centers surrounded by a chemical called 2-bis 2-pyridinomethyl 2,2-bipyrrolidine, which we will call BP-BP, structures forming cages. These cages serve to properly position and coordinate these cobalt atoms, providing the molecule with the ability to absorb oxygen with great specificity. These halves are held together by a benzene ring in the middle, which is introduced at the end of our synthesis as terephthalic acid. This bonds the two metal organic frameworks together. This was performed because previous literature research has implied that this bonded mirror compound, it shows a greater affinity for oxygen than the two halves on their own. So here's a proposed 3D structure of our molecule. You can see the nitrogen groups in blue. They're important. I'll explain that later. The benzene rings essentially surround that hexamer with the two cobalts shown in purple. It's hard to see. The two center red oxygens in that hexamer are the ones absorbed and possessing the ability to desorb. Note in specific the two single bonds binding most of these benzene nitrogen rings to the cobalt centers. This gives them flexibility, allowing them to twist, and that'll be explained why that's important in a few slides. At room temperature, as mentioned before, this crystal is a hydrate. It's a heptahydrate of the nitrate salt, meaning that it's coordinated with 7 water molecules in the natural crystal state. At this temperature, it will also aggressively absorb 2 diatomic oxygen gas molecules by forming bonds with the cobalt, which is at this point believed to be in the 3rd oxidation state. Upon heating to 80 to 100 degrees, it will lose these oxygens and 5 of the 7 water molecules, becoming a bihydrate. Its crystal structure stays mostly the same, although the cell diameters change. Critically, both hydrate phases form crystals which are nanoporous, allowing the migration of oxygen gas and water vapor into a bulk solid. That's critical as we need multiple grams of our product to function as intended. So the mechanism of action, here we can see the active cobalt center. The mechanism of absorption is critically dependent on the spacing of these cobalts and the positioning of the surrounding organic ligatures. This is the case with most metal organic frameworks, which show reversible gas absorption. The cobalt ions are held at the perfect distance to bind and hold this diatomic oxygen, binding O2 with great specificity rather than binding nitrogen, hydrogen, although this can be changed to produce different metal organic frameworks to absorb these other gases. At room temperature, as mentioned before, they're in the 3rd oxidation state, bonding readily with the oxygen gas. Upon heating, it was theorized that they convert to the 2nd oxidation state of cobalt, releasing the oxygen. The current theory put forward by most literature we read on the subject is that the nearby nitride groups in these benzene rings, being flexible, can bend inwards towards the cobalt centers and give the negative charge needed to stabilize them as they transfer states. I'll pass this back to Hannah.
So after the synthesis of the crystal, we tested our oxygen desorption and absorption capabilities using a Sievert's apparatus. The Sievert's apparatus is a piece of equipment commonly used for hydrogen absorption testing. The apparatus uses a piezoelectric sensor to detect pressure changes within a chamber after increasing the temperature. Before testing the crystal within the chamber, the sample was allowed to absorb oxygen at room temperature overnight to fully saturate the crystal. And this is where it also absorbed the water vapor. And this is also where it absorbed so much water vapor that it was able to pull it right off of the dry. So 60 milligrams of the sample was then put into the Sieverts chamber, and the heating temperature was set at 100 degrees Celsius, and this was run for 24 hours. The figure on the slide shows that the final plot for the desorption and water from the crystal. The peak seen in red is the total desorption of the absorbed species, which is both the oxygen and the water. Based on the ratio of absorption between oxygen and water from the paper, a final value for the mass calculated of oxygen desorbed was at 0.669 milligrams of oxygen desorbed, and that was for the 60 milligram crystal. As you can see, there's a dip in the graph after the initial peak, which we can attribute to water vapor condensing on the sides of the chamber and reducing the water vapor inside of the chamber. Next slide. And it also remained for a 24-hour run, stable after that. So here are the final desorption statistics. For the desorption run of the crystal, the total mass desorbed was 1.16 milligrams, 0.669 milligrams of which was oxygen, and 0.941 milligrams of which was water vapor. The mass of oxygen calculated was equal to about 0.502 milliliters of air at room temperature for that 60 milligram sample. This equates to a total absorption ratio of 7.72 microliters per milligram of crystal, which is about half of the 15.6 microliters per milligram that literature has provided. Additional testing would be required to determine why there is such a large discrepancy between the two numbers. The next test is the reabsorption of the oxygen after reducing the temperature in the chamber back down to room temperature. The graph shown above shows that approximately half of the desorbed oxygen was reabsorbed back into the crystal. This is far removed from the crystal synthesized in the literature. The crystal should have reabsorbed all or almost all of the desorbed oxygen. We have hypothesized that this is because there is such a high concentration of impurities within our crystal that there may be some alternative reactions going on that may be binding or releasing oxygen that we don't know. Further characterization testing, such as FTIR, will be it will be a next step for us to determine what kind of impurities are in there and why our oxygen has not been reabsorbed as much as we thought it would be. It is also noted that there was no color change between the two crystals as seen in literature, and we also attributed this to some impurities or imperfections in our synthesis technique that may be hammered out in another run. Another step for this project would be to perform some basic mechanical testing of our PDMS membrane just to make sure that it's safe to be used, handled by a user or a company. So this would be either tensile testing or impact testing to make sure that we can have proper testing of our safety seals.
So in summary, we did observe the basic mechanism expected from our product, which was the reversible absorption of oxygen and water vapor. The cost was kept relatively low for an experiment like this at around $21 for 60 milligrams of product. This cost is strongly hampered, however, by the extremely small quantities we could produce. Scaling up production would lead to a much decreased cost for the obvious reasons, especially with the time and equipment to synthesize our costliest precursor, bipyrrolidine, from simple monomers. We purchased this due to a lack of time and equipment to prepare it in the lab, but if you could produce this in an industrial setting, you could likely start with nitrated benzene rings. Under the conditions available, as mentioned, our product did not reach the full yields mentioned in literature and failed to resorb all of the oxygen gas it released. This is most likely, again as mentioned, due to the impurities in our final sample. These impurities could have been generated by a number of points in our synthesis. One major point that we think could have strongly affected the crystallization of our cationic core is we used heat evaporation in our final step as opposed to the vacuum evaporation due to limitations in our glove box. Some other points of potential issues were that the glove box and equipment used, while adequate for our small amounts in this initial test, were being used at the same time for other experiments and had many potential sources of contamination. There were vapors which we could not purge from the air. We were using washed glassware, but some of the samples prepared previously had been metal hydrates, which were particularly hard to clean off glassware and metal tools. Finally, the sample chamber used in the Sievert's apparatus suffered from the same failings. It had been used extensively for these metal hydrate tests, and it's almost certainly had some contamination still remaining, which may or may not have reacted with our product or impurities. Finally, the copper walls of the sample chamber may have actually interacted with our sample or the impurities. We theorize that these impurities may have either attacked our crystal when it reached higher temperatures, or that they would have irreversibly bound water or oxygen gas, affecting our results. With cleaner, more precise instruments and conditions, as well as multiple synthesis and characterization steps, these impurities could almost certainly be reduced or eliminated, increasing the efficacy of our product. This prototype has proven, however, that the base materials and methods are not out of reach for synthesis in relatively small labs with moderately complex equipment. Further research into this crystal or the related metal organic frameworks containing cobalt could produce a useful, versatile, and reliable tool to control oxygen concentration, both reducing and increasing, in a huge variety of chemical reactions and industrial processes. Thank you. Yes?
So you made a crystal yourself?
Yeah, we synthesized the crystal. We started, the largest monomer we started with was... Yeah, we prepared that. So the largest structure we started with was bipyrrolidine, which has changed here. I can't really show you. It's essentially a benzene, nitrogenated benzene ring and nitrogenated pentane ring bonded together. Starting with that, we fused this using 2-picoyl chloride into our BP-BP. We then introduced the cobalt into this BP-BP as a salt, where it was readily taken up in a cage structure. And finally, we used terephthalic acid to bond these two at a specific point.
So you characterized by the crystal product?
No, we actually did not. We only produced a very small amount of crystal, and due to the limitations of the lab and our budget, we were only able to do the Sievert's testing so far.
So how do you know that is what you want?
Our main indication is the fact that we saw a resorption of oxygen gas. The desorption was a good initial hint.
So this is the property, the structure, the material structure, any effort you have done.
Yeah, we still have to do characterization. We were hoping to do TGA testing as well as XRD to determine the crystal size.
Chemical structure.
Yeah, the TGA would give us the chemical structure, and then the XRD would give us the crystal structure, which we could compare against values from the literature.
So you want to know your chemical structure. You see something similar with what you show here.
Mm-hmm.
So crystal, you may not be able to characterize crystal, but any other technique you can see.
We were also thinking about using Raman spectroscopy to check the number of bonds and bond lengths. Yeah, we were going to use these three, but budgetary and time restrictions. One of our chemicals, 2-picoyl chloride, which we needed right at the start, was sold out in North America for about 3 weeks. That set us back significantly. We're planning to do this testing for the final report. Sorry?
Yeah,
Oh,
FTR
yeah.
was one that we were going to, if we had the budget, to perform after.
Yeah.
We chose to do the Sievert's apparatus instead of the FTIR because it provided us with at least a proof of concept that it had done something. So we chose that instead of the FTIR for that purpose.
Yeah. Our supervisor, not only did he have the sieverts apparatus, but he recommended to us that proving some rate of absorption and desorption would be more valuable to us in the limited time we had than characterizing the material itself.
Yeah, but if you do some scientific calculation, otherwise,
Definitely.
What kind of material working?
Definitely. We did have this set aside in the budget, and again, it was the time constraints that led to this being omitted from this presentation.
Maybe I'll ask a couple of questions. Some of my questions were along the same lines, but you know, the other one. So is this really metal organic framework?
Yeah.
Like, how do you define metal organic framework? It's a different meaning. In fact, this is a molecule. You know, how do you know that this forms really the extended structure of a metal organic framework?
Again, we're relying on the literature heavily for that. They characterized a number of crystals similar to this, and we selected the one that appeared to have the best oxygen absorbing properties.
Right, but what I'm saying is the metal organic framework is essentially a metal oxide, cores that are then, connected with the network of conjugated chain molecules, ionic molecules. And this doesn't seem to be, is exactly that. To me, this is more kind of, aromatic ring conjugated, metal organic molecule.
Yeah, that's correct.
Organometallic.
It is. It's a large organometallic. The literature referred to these in multiple papers as metal organic frameworks.
Some of them may, but that's I think that's a wrong,
wrong classification
of a molecule like that. Okay, so if you look at the metal organic frameworks as developed, for example, by Omar Yagi or Jeff Long or whatever, Joe Hop, they have really very different structure in terms of their extended structure. They have certain surface area that characterizes them in terms of that sort of networking of the organic molecules connecting these metal
So they're essentially polymers.
They're more like networks.
Networks?
Really.
Okay.
You can kind of look at them as polymers, but they're really sort of networks.
Okay.
And the reason why they have such high surface area is because these metal oxide cores are connected essentially with single chains of polymerized molecules, organic molecules.
Okay.
So to me, this is much more like really an organometallic molecule.
Okay.
Than metal organic framework. Okay.
We can also do some more research and to figure out how better we can describe our, after we do characterization testing, and we can, as you said, it's probably not the network that we can get.
That's the image. Where you get this image?
This was straight from the paper.
Yeah.
This is straight from our synthesis paper.
This is not the part of the framework.
It is a standalone molecule.
It's a standalone molecule, I think. It's a standalone
Yeah.
molecule. I mean, you can probably, as they said, you can take two parts and then you connect them, but actually then when you do that, you have a standalone, a complex molecule, but
So
standalone.
after your synthesis, what you have, what you see?
We had a crystal, like a dark purple crystal. When left overnight, it again aggressively absorbed the water and kind of.
So after you mixed everything, you get a crystal or precipitate?
We had to dry it and to get the precipitate, which is the crystal.
I'm not sure what exactly, yeah.
So how do you crystallize it then, though?
We due to constraints in our glove box, we couldn't pump it down to a full vacuum. We had to use heat to evaporate it, which was not recommended or ideal. They wanted vacuum evaporation, so we figure we may have damaged the structure, or the terephthalic acid might have dried too quickly to connect all of them, leading to impurities.
Yeah, that's why I'm asking, because crystallization is not necessarily an easy process, especially if you want to do single molecule crystal structure on it.
Yeah.
It's not something that you do under heat.
Yeah. Another, in reference to your earlier comment, another reason they might have called it a metal organic framework is because that central ligature, they experimented using different groups. So they essentially attacked different attached different functional groups to that benzene ring and experimented with a variety of, like, one case used 2 nitride groups branching out, another used extra methyl groups coming out.
It's questionable whether this falls into the category.
Yeah,
of metal organic
yeah.
framework.
We're
It's a very specific class of materials that certainly, you know, would not appear as specific molecular species like this.
yeah.
This is more like routine BP that you use for, say, dye-cooperated, solar cells and things like that, which is really a molecular species.
Yeah, it essentially is. We just took their
So
word.
let me ask you one final thing. Given that you have a change in color before and after oxygen absorption, give me one effective tool that could be easily applicable and tell you a lot about at least behavior of the metal species with this molecule.
One application of this,
Or one testing method?
One testing method, yes. Characterization method, testing method, electronic structure.
The first one that jumps to mind for me beyond basic light microscopy to confirm this would be the IR or UV spectroscopy we mentioned before. So you could check the number of bonds
Essentially, but UV
before
what?
and after.
Okay, UV spectroscopy, there are all kinds of UV spectroscopy. What type of UV spectroscopy?
Raman spectroscopy to measure bond lengths.
Raman is not UV usually. It's a vibrational method.
you can use UV vis, but then the
UV
only
is what?
sure.
Sorry.
It's true UV vis, but UV vis absorption spectroscopy.
Oh yes, absorption.
Right, because you're
Yes.
essentially, the color that you see is associated with your
With
metal centers.
absorption.
So cobalt 2, in general, in this case, it's what? It's 4-coordinated, right? Is that 4-coordinated without?
Without the oxygen,
this sort of quasi-tetrahedral.
yeah,
Distorted tetrahedral.
stabilized by
That's
those
generally
nitrides.
The bluish region, so that's the typical quartet transitions associated with that cobalt
Okay.
species. And then as you change the coordination, obviously your color will change because your ligand field
Right.
transitions would
Okay.
change
Would it-
together with the change in geometry.
That's a very useful method actually. We had
Would it be possible to do UV vis absorption because our crystal is kind of hard to have in water?
that is a problem.
Yeah, because the techniques that we're used to for UV vis is just dissolving or diluting in water and then using the UV vis like that, or diluting in another solvent.
Oh, if you can dissolve this, then it's very easy.
The
That's
problem
that's
with
the
it
problem.
is its absorption capabilities decrease about 100-fold in solution for really unknown reasons at the moment. The solid
So
nature of the
color
crystal
needs to be intensity based?
is critical. Yeah, we would
So
need,
it would be a little bit difficult because we would have to have the crystal desorb the oxygen to turn the pink color, and then we'd have to find a way to measure that before it starts to absorb oxygen immediately. So
Okay, so basically you would have to somehow incorporate it in some inert medium that would
You're right.
allow you to
that
measure.
Yeah.
would allow.
Yeah, of course, all of that represents technical experimental
Right.
challenges,
Right.
but not unheard of. People do
Yeah.
that, seal it in different types of cells. If you can't dissolve it, you can do diffuse reflectance, which is basically sort of, measuring absorption spectrum in the sort of reflective mode, which
Okay.
can also be done, right? It requires sort of an addition to the instrument, but it can be done. And I think a lot of the speciation associated with, oxygen binding to your metal centers can be inferred, if you know
Yeah.
ligand field theory and how to interpret the data, of course, very helpful.
Yeah. That's actually a very useful method we hadn't particularly considered.
Right. Well, anything that is colored, your absorption should
Yeah.
be your first idea.
True. True enough.
That helps essentially in the visible region, basically. That's what changes.
Okay.
Color.
Yeah. All right. Thank you.
Okay, thank you guys.